Okay, so this talk is about quantum proofs of deletion for learning with errors. And specifically, I'm going to talk about quantum encryption with certified deletion. So this is a really new and exciting idea in quantum cryptography. And the basic idea is the following. You have Alice and Bob. And what the scheme allows you to do is to encrypt a plaintext M and send a ciphertext to some party, say Bob, in such a way that at some point later you can basically ask this party, say Bob, to delete the ciphertext for you. And in this case, Bob will produce a classical certificate pi, and Alice, using her verification key, can basically check if pi is a valid deletion certificate. And if that's the case, then Alice will be convinced that Bob has deleted the ciphertext. And certified deletion security says that you can even reveal the secret key at this point. Bob still cannot tell which message was encrypted. Okay? Really, really cool idea. And this is due to Broadbent and Islam, who gave the first private key encryption scheme with certified deletion. And the scheme that they proposed is very much inspired by the QKD protocol. So you have BB84 states, you have randomness extraction, and a one-time pad. Okay, and notice that this cryptographic construction only works using quantum information, because obviously, classically, there is no way to convince someone that you deleted a ciphertext. So how can this possibly work? Well, quantum information has this really nice property that there exist mutually incompatible bases in which you can measure. Okay, and Broadbent and Islam exploited this property and basically said, look, if you want to delete a quantum ciphertext, then show me a Hadamard basis measurement outcome. Okay, and obviously the information that's required to decrypt will not be in the Hadamard basis, it'll be in the computational basis. And we know that you can't measure in both bases at the same time. Therefore, once you report an outcome that's that passes as a Hadamard basis measurement, you must have uncertainty about a computational basis measurement outcome, and randomness extraction allows you to kind of bootstrap this into statistical randomness that hides the plaintext. Okay, that's kind of the main idea. And Hiroka, Morimai, Nishimaki, and Yamakawa later extended this to public key encryption and attribute-based encryption. And the scheme that they used is a hybrid encryption scheme. So basically, the idea is you take Broadbent and Islam's scheme, and this will be your quantum part, and then you add a classical part, which is just a classical encryption of the private key of the Broadbent and Islam scheme. Okay? And this way, you can easily get public key encryption. It's a really simple idea, and even attribute-based encryption if you use something called non-committing encryption. Okay? It's required for the security proof. And this is how hybrid encryption basically works. Okay, you take a private key encryption scheme with certified deletion, and you kind of extend it to public key encryption and so forth. Okay, and if you delete the quantum part, then the classical part should reveal nothing about the plaintext, for example. Okay, so this is very nice. What's kind of missing in the construction so far is functionality, right? Because if Alice sends a ciphertext to Bob, then Bob can hold on to it and at some point delete it, but there's no functionality that's kind of involved here. So one thing that's still open is to construct a fully homomorphic encryption scheme with certified deletion. And this kind of adds functionality because now you can imagine that there's a server and a client, and the client wants to send the server some encrypted data, and the server wants to apply some function to this data, some computation, in such a way that later when the server returns the outcome, the client can learn kind of the outcome of this computation, but then still request that the server afterwards deletes all possible data, okay? So at some point, the client learns the outcome of the computation and can then ask the server to delete everything and to prove that there's no information left. Okay, unfortunately, hybrid encryption is not good enough for this task. And the reason is that once you have homomorphic encryption, then you can always decouple the classical part from the quantum part, okay? So somehow hybrid encryption is kind of fundamentally insufficient for this. And if you're interested in the details, you can read the introduction of my paper where I describe how this attack works. So somehow to construct FHE with certified deletion, we need an all-new approach that doesn't use hybrid encryption, okay? And this is kind of the contributions in my paper where I give a new construction that doesn't follow this hybrid paradigm. And the way we're going to use it, do it, is we're going to construct a encoding which allows you to prove deletion of a learning with error sample. And once you have that, you can basically construct, fully homomorphic encryption based on that idea alone. Okay, so this is how we're going to do it. We're going to use LWE specifically because we know that LWE is very versatile, and I'm going to briefly remind you about some basic facts about LWE, and then I'm going to show you the encoding. Okay, so LWE is kind of our favorite hardness assumption for post-quantum crypto. We think that there's no efficient quantum algorithm that solves LWE, and we can do public key encryption, and we can do lots more that we don't really know how to do under any other assumptions like FHE or quantum verification. And the problem is easily described as follows. So LWE is kind of a decision problem, and the assumption says that it's indistinguishable whether I give you a random matrix A and a noisy vector S times A plus E, where E is a Gaussian error term that smudges all the information about S, or I give you a random matrix A and a random vector U, okay? And those two samples should be indistinguishable. And if you believe this assumption, you can build all sorts of fascinating crypto from it. And LWE is related to lattices, and specifically, it's kind of an average case bounded distance decoding problem. Okay, so now we know what LWE is. How do we delete an LWE sample in a way that convinces a verifier? And the main idea is the following. We're going to use Gaussian states, and specifically, we're going to use states that kind of occur naturally in a quantum reduction from SIS to LWE, okay? And this is kind of a reduction that's implicitly already in Regev's original work, and was later given in a paper by in the SSTX paper, where they gave an explicit quantum reduction from SIS to LWE. And the states that are involved in this reduction are exactly the states we need to use for our certified deletion protocols. And here's the idea. So we're going to start as follows. We have an LWE matrix A, and one state we can construct is the following Gaussian superposition. Okay, so we take a superposition over Gaussian vectors X, and then we're going to compute A times X in another register. Okay, and A is our LWE matrix. And this state by itself is not very interesting yet, but if we measure the second register, we get a random looking outcome Y, and something really interesting happens. We get a superposition of solutions to the equation A times X equals Y. Okay, and this is the state on the left-hand side, which I call the dual state. Okay, and once you measure the state, you get one short solution. And specifically, you get a solution to the so-called inhomogeneous SIS problem, okay? So this is a short solution to the equation A times X equals Y. And what's really cool about the state is that if you apply the Fourier transform, you get a new state, which I call the primal state. And the primal state is a superposition of random LWE samples with a phase that depends on S and Y, where Y is kind of the image that we obtained by collapsing the state. Okay, so those two states are extremely useful, and it's kind of also already clear how we're going to use this for deletion, right? So let's look at the state on the right-hand side, the primal state. So here we have LWE, so we can use this basis, or the kind of primal domain, to encode the ciphertext. Okay, we have LWE, we can shift it, we can encrypt. So this is where the ciphertext will be encoded. And if you Fourier transform this, then you get the dual state, which you can measure to get short solutions to some equation. Okay, and this is exactly how we're going to do deletion, because you can't measure in both bases at the same time, right? Because the Fourier bases and the computational bases are incompatible. So in order to prove deletion, I will ask you to measure in the dual domain and show me a short solution to some equation that's specified by A and Y. And if you show me a pre-image, then I can be convinced that you deleted the ciphertext information, which now will be encoded in the phase. Okay, so on a high level, this is exactly what's going on. And LWE is great for this because we're using the structure of LWE. Okay, here's how I'm going to kind of bootstrap this idea into an encryption scheme. And this is the Dual-Regev public key encryption scheme. Okay, and once we have that, it's fairly easy to get FHE. Okay, and the idea behind this public key encryption scheme with certified deletion is that there's a public key, which is a matrix A, and the matrix A is sampled with a trapdoor. Okay, so T is a short trapdoor vector in the kernel of A, and this will be our secret key. And in order to encrypt, you basically just generate the following ciphertext and verification key. So the verification key is just specified by A and Y, where Y is a random image. And the ciphertext is the primal state, right? It's just a Gaussian or say a superposition of random LWE samples with random S and Gaussian E. And because we want to encrypt, we just shift it by something that depends on B, exactly like in the classical Dual-Regev scheme. And this is our ciphertext, okay? And decryption is also exactly as in the classical Dual-Regev scheme. We just use the trapdoor to recover B. Okay, so how can we use this for certified deletion? Well, we're going to do exactly what I described before. We're just going to apply the Fourier transform if we want to delete. Once we apply the Fourier transform, we get the following state, which is a superposition of short solutions to AX equals Y with a phase that depends on B. But in order to delete, I want to see a pre-image, or I want to see a short solution to the ISIS problem, or inhomogeneous SIS problem, A times pi equals Y. And if you send me a certificate pi, then I'm just going to check if it is a short solution. Okay, and if that's the case, then probably you must have measured the state. And if you measure the state, the phase is gone, therefore the ciphertext is gone once and for all. Okay, and what's nice is that this is publicly verifiable, right? Because I can hand out A and Y, and now anyone can check whether you deleted the state by just checking if they gave you a short solution to this equation. And we know because the ISIS problem is hard, and it's related to worst-case lattice problems, it will be computationally difficult for you to find such a certificate without measuring the state. Okay, and that's kind of the whole idea. And to get FHE, we use a very similar scheme that follows exactly the same paradigm. So we're just going to use something called the dual GSW scheme. So this is by Gentry, Sahai, and Waters, and was also used by Mahadev, who kind of used the dual variant. And here, everything is exactly as before, except now we use matrices rather than vectors. And in order to encrypt, say, a bit X, we shift by X times G, where G is something called a gadget matrix that has something to do with bit decomposition. Okay, but everything else is the same. And decryption is also exactly as in the classical Dual-Regev scheme. We can delete and verify exactly as before. We can just measure in the Fourier basis, which will give us many solutions to certain ISIS problems specified by A and some vectors Y. And we can also do homomorphic operations because this is exactly the dual GSW scheme. So we can apply homomorphic NAND gates in superposition, essentially. And the NAND gate is universal for classical computation. So we can essentially, obtain a leveled FHE scheme this way. And there's one tricky part, namely, if you want to compute an encrypted data and also prove deletion, then you need one additional round of communication and some rewinding argument that's kind of missing in the standard FHE scheme. So in the standard FHE scheme, at the end of the protocol, the client learns the outcome of the computation. And in our scheme, to prove deletion, you just need one extra round. And in this extra round, the client effectively has to return some quantum state to the quantum server. And then afterwards, the server can actually complete the protocol and prove deletion. And this requires a kind of rewinding argument that I explain in the paper. But then once this is complete, the server has no information about the data anymore, and the client has learned the outcome of the computation. Okay, this is kind of exactly what we want. Obviously, there are a few details that I can't go into in my talk, but yeah, feel free to read about them in the paper. Okay, so I haven't at all talked about security, and this is where something which I call Gaussian collapsing hash functions comes in. And it's maybe at this point unclear what this has to do with security, but I'll explain it more in detail now. So it turns out that security is related to something that people call collapsing when they talk about properties of hash functions. And this is something that was introduced by Unruh in 2016, I believe. And collapsing means that it's indistinguishable to, or it's computationally difficult to distinguish superpositions of preimages from measured preimages. And in my paper, I consider a special case of it, which I call Gaussian collapsing. And it's obviously a special case. It's weaker. It has to do with Gaussian superpositions. But it turns out that this is really natural when you work with LWE and SIS. And in my paper, I show that the itai hash function is Gaussian collapsing under LWE. Okay, I give a very simple and direct proof. And basically, the property means that no computationally bounded adversary can tell if it's given a superposition of Gaussian preimages or a single measured preimage x0. Okay? And so how does this come in, and how does this compare with the schemes that I described earlier? Well, if you take the Fourier transform of both of these states, then you know that these states below are also indistinguishable, right? Because of the top, if the states at the top are indistinguishable, their Fourier transforms must also be indistinguishable. And now the state in the bottom left corner is exactly the state that we're using to encode ciphertexts, right? So now we can use pseudo-randomness of the state, and we know that it's computationally indistinguishable from a uniform superposition with a pre-image in the phase. Okay, and under LWE, these two are indistinguishable. So this argument allows us to get CPA security of our scheme. But for certified deletion, we need something a little bit stronger, right? We need the property that once you delete, even if I give you a secret key, you cannot tell which message was encrypted. And the secret key is always a short trapdoor vector, okay? So this brings us to a stronger version of Gaussian collapsing. And unfortunately, I don't know how to prove it under standard assumptions. So instead, I kind of state it as a conjecture. And it's a very plausible conjecture, and it basically says the following. So we can prove the security of all the protocols in my paper under this conjecture, and it's a very simple experiment, and it works like this. So there's a challenger and an adversary, and the challenger flips a coin, and this coin is some outcome B, which is either 0 or 1, with probably 1/2. And if B is 1, then the challenger uses the following state. It's a Gaussian superposition of pre-images to some equation, AX equals Y. And if B is 1, then the challenger measures the state and instead uses a single pre-image x0. Okay, and the challenger sends the state to the adversary. So it's one of the two with probably 1/2. And the adversary also gets public information A and Y. Okay, now the challenger wants to see a pre-image of AX equals Y, or some pre-image pi that satisfies AX equals Y. So the adversary generates this pre-image pi somehow, and we don't care how the adversary does it. All that matters is it sends one such pre-image to the challenger, and the challenger will check if it's valid. Okay, the challenger checks, is pi short, and is it a solution to this equation? In other words, is pi a ISIS solution for A and Y? And if that's the case, the challenger will actually send the adversary a trapdoor for the matrix A. And if it's not valid, the challenger will just abort. So now the adversary actually has a trapdoor, okay? In other words, the adversary can now have some non-trivial information about the states beforehand, but the adversary has already shown us a pre-image, so the adversary must have already measured, right? Because how else could the adversary get such a short pre-image? We know the ISIS problem is hard. So the idea is, once you show us one pre-image, I might as well give you a trapdoor, and you don't know whether at the beginning of the experiment you started with a superposition of pre-images or with a single measured pre-image, okay? Once you show me a pre-image, it's already too late. I might as well give you the trapdoor. Okay, and the claim is that those two are indistinguishable. And unfortunately, I don't know how to prove this under standard assumptions. And I give some, maybe some ideas how one could prove it. And I also give something called an entropic uncertainty relation that rules out a large class of natural attacks that could break this conjecture. Okay, so this brings me to the summary. So here are the main contributions in my paper. So I show you how to use quantum superpositions of LWE samples as a promising way to get certified deletion protocols in a non-hybrid manner, okay? The second contribution is Gaussian collapsing hash functions, and this turns out to be supernatural when you work with LWE and SIS, and it's strictly weaker than collapsing, right? It's a special case. And Gaussian collapsing as a property of hash functions may be useful for other cryptographic primitives. And then I gave two encryption schemes with certified deletion, a Dual-Regev public key scheme and a Dual-Regev leveled FHE scheme. And I proved deletion under the strong Gaussian collapsing conjecture. So here are two open problems that I personally find really interesting. So the first is prove the strong Gaussian collapsing conjecture, for example, under standard assumptions like LWE or the ISIS assumption, or disprove it if that's the case. The second open problem that I also find interesting is to just dequantize all the communication between the classical client and the quantum server, and to just get a classical client quantum server type protocol. That would be really fascinating if that was the case. Okay, that's the end of my talk. I hope you have interesting questions that you can always send me by email if you like. Okay, thank you for your attention.